right, trigonometry, starting here on page 562. Now, the hardest part about trigonometry is getting over the vocabulary. All right, trigonometry sounds difficult. It's not, especially when you break it down and see what it actually means. It says the word trigonometry comes from two Greek terms, one meaning triangle and the other meaning measure. So triangle measures. What have we been doing the last few weeks? Triangle measures. All right, so it's just another tool doing the same kind of thing. Right triangles especially, we know a lot about and we can work with really well. If we know two sides, we can Pythagorean theorem, find the third side. If we have a special right triangle, 30, 60, 90, or 45, 45, 90, all we need to know is one side, and we can figure out the others. So now we're going to get to where with any right triangle, if we know one of the acute angles and a side, then we can figure out all the other sides. Okay? So we're getting to where we're able to generalize it more and work with more different right triangles. We can work with all of them now. Well, at least after we're done with this section, we can. Okay? Now, a trigonometric ratio is a ratio of the lengths of two sides of a right triangle. All right. Well, look, every triangle has three sides, so making a ratio out of two of those sides isn't all that bad, is it? So look, if we look at this one right here, if angle A is our focus, so the vertex of angle A is point A. So let's think about point A. We've got two legs, and we've got a hypotenuse. Well, I know which one's the hypotenuse. It's that one. Now, our two legs. Depending upon how big angle A is, you know, the short leg might be across from it, or the short leg might be adjacent to it. So let's not get into short or long. Let's just deal with this. We can call that one the opposite leg, and we can call that one the adjacent leg. Now, when we write these abbreviations, op, edge, hype, what we really mean, and I'll say this a lot, but I won't say it every time, is we mean the length of the hypotenuse, the length of the opposite leg, the length of the adjacent leg. It just gets monotonous saying that over and over and over, so we shorten it. Opposite, hypotenuse, adjacent. Okay? Notice that adjacent is for a leg. Because look, the hypotenuse is also adjacent to point A, isn't it? But we don't call it the adjacent leg because it's not a leg, it's the hypotenuse. So opposite means leg, adjacent means leg. Okay? Now, couldn't we do this, the same kind of labeling for this 35-degree angle here? We'd get opposite over there, that'd be the hypotenuse, that'd be adjacent, and for this 35-degree angle here, opposite would be over here, adjacent over here, hypotenuse. So, if we wanted to, and by the way, since all three of those triangles have a right angle and a 35-degree angle in them, what's true about those three triangles? They're all similar by angle similarity, aren't they? Okay? So they're all similar to each other. So look, if I take the top one up here, well, any of them actually, if I make a ratio out of the opposite leg to the hypotenuse, and then I move to a different triangle, and I make a ratio out of the opposite leg to the hypotenuse, then I move to the third triangle and make that same ratio. What's your guess about those three ratios?
They're going to be similar or congruent.
They're proportional. In other words, the ratios are equal. Okay? Those corresponding these ratios out of opposite and hypotenuse are going to be proportional, so the ratios are equal. So those ratios are equal to each other. Now look, I can get a little bit fancy as to why. When we've made proportions in the past, if that was the ratio of a pair of corresponding sides, and that was a ratio of a pair of corresponding sides are proportional, so those two ratios would be equal. The very first time we talked about ratios and proportions, I don't remember if it was somebody in this class or one of the other classes, but somebody said something like, hey, I wrote mine upside down from yours. Is that okay? And I gave a kind of a non-committal answer of, yeah, but let's not do that. It is perfectly okay, right? In fact, if I even did this, or this, all four of those proportions are saying the exact same thing. Here's how I know why. When I do cross products, don't I get that for all four of those? So they're all the same thing. Now, they didn't suit our purpose at the time, which was to match up corresponding sides, and it would get confusing if you had too many options. All right, so that's the reason I told you to stick with that. Just stick with, short to short, long to long, that kind of thing. Okay? Not because I was trying to cheat you out of knowledge, but it would have been more confusing then than I hope it is for you now. Here's what I'd like for you to notice. If A to B is a ratio of a pair of corresponding sides, and C to D is a ratio of a pair of corresponding sides, when I make this ratio, A and C came from the same triangle, didn't they? And B and D came from the same triangle, didn't they? So that wouldn't have gone over too well a week ago, would it? That would have been confusing to say, well, you can make the ratios from the same triangle if you want to. Ugh, bad news. But now that we're looking at trigonometry, look, we can. So this idea of opposite over hypotenuse, where both those sides are from the same triangle, it works because there's more than one correct way to write a proportion when you have similar triangles or similar anythings. There's more than one way to write the proportion. That's one of them. Opposite to hypotenuse equals opposite to hypotenuse. Okay? Well, look, that's one way I can do a ratio. I could also make a ratio out of adjacent to hypotenuse. And if I did that for all three of those triangles, since they're similar, I'd get the same ratio every time. And I can even make another ratio of opposite to adjacent. And if I do that for those three triangles, since those three triangles are similar, that ratio of opposite to adjacent will be the same every time. So, every time we've got a 35-degree angle, we don't have to redraw the triangles and start figuring out sides. Those ratios of opposite to hypotenuse, that's the same for every 35 degrees. The ratio of adjacent to hypotenuse is the same for every 35 degrees. Now, I'm not saying that that ratio equals that one. I'm not saying that. I'm saying opposite over hypotenuse equals every other opposite over hypotenuse for a 35-degree angle. Adjacent over hypotenuse equals every other adjacent over hypotenuse for a 35-degree angle. Opposite over adjacent equals every other opposite over adjacent for a 35-degree angle. Now, what we need now are names, because we're going to use these. We're going to use these a ton. And we don't need to be saying, hey, remember how we said that the opposite over hypotenuse ratio is always the same? We need a name for it. So here are the names. This one is called sine. This one is called cosine. And this one is called tangent. Now, you don't even have to write that down yet. I'm going to tell you when you have to write it down. You can if you want, but you don't have to. The book does a pretty nice job of charting this for us here on page 562. They put way too many words in, but that's okay. The sine of angle A, written. Now, it's called sine. Its abbreviation is just 3 letters, but don't call it sin. It is not sin. It is sine. All right? So that's the way you write sine, and it is equal to opposite over hypotenuse. We won't worry about angle B yet. The cosine of angle A written as cosine of A. Don't call it cos. It's not called cos. Be grateful they allow us to abbreviate it in writing. We don't abbreviate it when we say it. It's cosine A. Well, that's our name for adjacent over hypotenuse. We won't worry about B. And then the tangent of angle A is written as tangent A. That's the one that's opposite over adjacent. And I won't worry about B yet. So what you need in your notes is this right here. The sine of A equals opposite over hypotenuse. The cosine of A equals adjacent over hypotenuse. And the tangent of A equals opposite over adjacent. All right, you've got to memorize those. You've got to memorize them today because we're going to use them and use them and use them and use them, and you've got to know them. Now, here's one little trick to help you memorize. And unfortunately, I don't have a very good memory, so I don't remember the story behind this. There's supposed to be some story I'm supposed to tell you about an Indian named Sokotoa. I don't remember the story. I just remember the name. S for sine, OH for opposite over hypotenuse. C for cosine, AH for adjacent over hypotenuse. T for tangent, OA for opposite over adjacent. I don't remember the story. But if I write that at the top of my paper, I'll never get these definitions wrong. Ever. Ever, ever, ever. So, if I were you, I'd memorize that as well. So, ka, toa. And one of these days I'll look up the story that goes with it and get back to you, but you'll probably have kids of your own by then. Google it. Well, no, because you never know what you're going to get when you Google it. You Google the most innocent thing and you get the most horrible things as replies and or as hits or whatever, and that's just, yeah. All right. Now, I've ignored angle B. And you don't have to redo your definitions to put a B in there because you can name the angle whatever you want. But look, in one right triangle, if C is your right angle and A and B are your acute angles, A and B are complementary to each other because the three angles in the triangle add up to 180. C is 90 of it, so A and B add up to 90, so they're complementary to each other. Now, if I'm thinking about point A, then, and by the way, this is common too. The leg that's opposite angle A is called little a. The leg opposite angle B is called little b. And the hypotenuse opposite angle C is called little c. That's where A squared plus B squared equals C squared comes from. That's the traditional way to label those. Okay? But if I'm here at point A, the opposite leg is called A. The adjacent leg is called B. The hypotenuse is C. And that gives me that, and that for my trig definitions. But what if I'm at point B? If point B is the focus, then A is not the opposite leg. A is the adjacent leg, isn't it? And B is the opposite leg. The hypotenuse stays C. That doesn't change. But when you switch from one of the acute angles to the other one, the opposite and the adjacent switch, don't they? So if the sine of A is A over C, the sine of B has to be B over C. And if the cosine of A is B over C, the cosine of B has to be A over C. Notice something here. Notice. Look at the screen. What's true about the sine of A and the cosine of B? They're equal to each other. Why are they equal to each other? Because the opposite and the adjacent switched. So the leg that's opposite A is the same exact leg that's adjacent to B. And then notice the sine of B and the cosine of A. What do you notice? They're the exact same thing, aren't they? Okay? So, the people that wrote our new math standards thought that was such a big deal, they made that an entire standard. Usually it takes us 4 or 5 learning targets to get a standard. I made their standard into a learning target, and I even had to add the word use. Okay? So that was a standard as far as the new standards go. Explain the relationship between the sine and cosine of complementary angles. I said we're going to use it as well. So I need you to write down everything there in blue. So write down, in one right triangle, the two acute angles are complementary. The sine of one of the angles is the cosine of the other, which I thought made perfect sense to me, but I was afraid wouldn't make perfect sense to somebody learning this. So, in right triangle ACB with right angle C, I named it that so it goes along with the one that they make this table out of. The sine of angle A equals the cosine of angle B, and the sine of angle B equals the cosine of angle A. I think all this will make more sense to you when we put some numbers to it instead of just letters. Okay? Now, we need more examples than just working a few from your assignment like I usually do. So what we're getting ready to do are from the Check Your Progress problems on page 563. You need to write these down. So they're not from the homework set of problems, but you need these examples. So we're now going to use our trigonometric ratios. And notice when I wrote the learning target, I put in and the Pythagorean theorem because I don't want you to forget that. That always works for a right triangle. Now, for the first couple of questions we do, it wouldn't come into play, but don't forget that. Some of you got caught short on the last quiz by forgetting that not everything was a 30, 60, 90, and you didn't use Pythagorean theorem. So don't forget good old Pythagoras, okay? But this problem here, number 1, is from the Check Your Progress on page 563. And I've copied down what we need to know. We need those definitions, okay? And they are definitions. The reason sine equals opposite over hypotenuse is because we say so. It's a definition, okay? So number 1, we want to find the sine of J, the cosine of J, the tangent of J, the sine of K, the cosine of K, and the tangent of K. We're going to express each of these ratios as a fraction, and if you want to change them to a decimal on your calculator, you can. Top divided by bottom. I'm not going to bother with that. We'll be doing some decimals later on. So first, let's find the sine of J, cosine of J, and the tangent of J. Well, then we look at our triangle. There's J. Before we try to write a ratio, let's label, I'm going to label them literally on the page. You can just do it in your head. Let's label what each of these numbers are. Which one's the hypotenuse? So, and for point J, which one's the opposite leg? So which one's the adjacent leg? Don't get adjacent and hypotenuse confused, because they both are next to point J, but the hypotenuse is the hypotenuse, and adjacent means adjacent leg. So don't get those confused. Well, look, now that I've got that, all I got to do is look at the definition to know what the sine of J equals. It'll be opposite over hypotenuse. So it'll be 5 over 13. What's the cosine of J? Adjacent over hypotenuse. 12 over 13. And the tangent of J, opposite over adjacent, 12 over 5, 5 over 12. Now, we need the sine of K, cosine of K, and the tangent of K. So hypotenuse doesn't move, but 12 is now the opposite leg, and 5 is now the adjacent leg, isn't it? So the sine of K, opposite over hypotenuse, will be 12 over 13. Cosine of K, adjacent over hypotenuse, 5 over 13. And the tangent of K, opposite over adjacent. All right. Now, the things we noticed before. The sine of J does equal the cosine of K, doesn't it? And the cosine of J does equal the sine of K. And the tangents are always reciprocals of each other. Always, always, always. Okay? 5/12 and 12/5 are reciprocals. Not opposite reciprocals, like with perpendicular lines or slopes, just reciprocals. Yep, sure could. Oh, we'll get there. All right, number 2. Use a special right triangle to express the cosine of 45 degrees as a fraction, and then again, if you want to do the decimal, you can. A special right triangle. What 2 special right triangles are we familiar with? 45, 45, 90, 30, 60, 90. Considering they're asking us about a 45 degree, I think they want us to talk about a 45, 45, 90. So we draw that. Now, since I'm making this triangle, I can make the lengths anything I want within certain parameters. The legs have to be equal, don't they, in a 45, 45, 90. And the hypotenuse has to equal the leg times the square root of 2. So I get to make up what I want the length of the legs to be. I could make up just the most horrific number in the world. You know, I could make it like 7 million something over, 20 trillion something. Or I could just make them 1. 1's pretty easy to work with, right?
Yeah.
So if each leg is 1, and they are equal, so I'm good there. What's the length of the hypotenuse have to be? Leg times square root of 2, 1 times square root of 2 is the square root of 2. All right. So use a special right triangle to express the cosine of 45. So square root of. Cosine of 45 equals. Now, pick one of the 45s. It doesn't matter. It's going to work the same either way. So I'll pick that 45 right there. What's the length of the adjacent leg?
1.
What's the length of the hypotenuse? Square root of 2. And we are done. So that's the cosine of 45. All right, now some of you have been toting around these expensive calculators for a year, and all you've done with them is add, subtract, multiply, and divide. All right, it's time for you to get your money's worth. If I do 1 divided by the square root of 2, I get that. If I just hit the cosine button and then 45, I get my answer that way. So, if you have a calculator with a sine, cosine, and a tangent button on there, today's your lucky day. If you do not, you may very well have a phone or an iPod Touch that does. Because you can find a free app for iPhones, iPods, Androids, where you have sine, cosine, and tangent on a calculator. Okay? If you don't have either of those, a calculator or an app, then you can share, because you're going to need those buttons. Okay? Now, one thing you got to make sure of. Let me do some little magic here. Close your eyes. You can't see this. This ruins the magic if you see it. Now if I type in cosine of 45, I don't get the same answer. All right. You've got your calculator in radian mode. There are two ways, actually there's more than two ways. There are two common ways to measure angles, degree and radian. And degree is far and away the most common. But look at the third row down there. I hit the mode button. That's the way it works on these TIs. Third row down, I've got radian highlighted. Highlight degree. Just cursor over, get the degree highlighted, and hit enter. And now when I do the cosine of 45, I'll get the right answer again. So, I don't know how all the calculators work, and I definitely don't know how all the apps work. But you've got to get yours set in degree, okay, and leave it in degree. Because if you get it set back to radian, you'll miss every single problem you use your calculator for, and that will be sad. It'll be funny, but mostly sad.
Oh, I figured out how to fix it. Sweet. Took me a minute.
All right. All right, let's flip over to 564. All right, you can work with your calculators in a minute. Let's keep going. Yeah. I'll show you how to use it with sides either tomorrow or the next day, though. All right, so we keep going. Now, to solve a triangle means to find the length of every side and the measure of every angle. Now, we're going to take baby steps to get there, okay? But we need to start working on that, being able to solve a right triangle. All right, getting the angles, if you know two of them, getting the third one's a piece of cake, right? So, I mean, we could do that for 3A and 3B right now, but we're not quite ready to do the whole thing. So, but let's work on finding x when x is the length of one of the sides. We need to know the length of one side and the measure of one acute angle. And if we know those two things, we're in business. So on 3A, we know the length of one side, we know the measure of one of the acute angles, we're in business. Here's how we're in business. If I'm going to find x, don't we almost always need to come up with an equation involving x? Okay? So that's what we're going to do. And how are we going to get an equation involving x? We're either going to use the definition of the sine of an angle, or the definition of cosine, or the definition of tangent. Now, what we know is that that angle right there is 25 degrees. So don't write this down yet. So I'm either going to start off the sine of 25 equals whatever, or the cosine of 25 equals, or the tangent of 25 equals. Well, the thing is, only one of them is going to work, because only one of them will contain the information I need it to contain. So look, from that 25 degrees, x is the opposite leg. 18 is called the adjacent leg. Does the hypotenuse have anything to do with this problem? Doesn't look like it. So guess which one I'm using? Tangent. Not because it's my favorite, not for any preference, simply because I need to know the opposite leg, and I already know the adjacent leg. Opposite and adjacent, that's tangent. So, the tangent of 25 equals opposite x over adjacent, 18. That is not the answer. That is the equation. I know how to solve that equation, and you're about to. First thing I want to do is get rid of the fraction. How do I get rid of the fraction? Multiply both sides by 18. So I get 18 times the left side equals, and what happens when I multiply the right side by 18? Yeah, I just get x, don't I? Because the 18 that I'm multiplying by divides out with the 18 in the denominator. Just get x. Well, you know, I didn't mean to, but I solved it for x when I did that, didn't I? That's not the answer. That's an answer. Because we can simplify that, okay, with our technology. So, 18, I don't even have to use a times sign. Times the tangent of 25. I do need to make sure I'm in degree. I am. That's what x equals. So 8 point, for now, let's round everything to the nearest hundredth. So that'd be 8.39 is x. Now, if you're one that always expects your answer to be a whole number, you're going to hate this section because your answer is almost never going to be a whole number. So you got to get over it. Well, it should make you more nervous when you get a whole number. Okay? All right. We okay with 3A?
Yeah.
Now we tackle 3B. All right. The 70 degrees, that's the angle I know. So, sine, cosine, or tangent, do you think? All right. If I write the cosine of 70, cosine is adjacent over hypotenuse. What's the length of the adjacent leg? Nope. 15. What's the length of the hypotenuse? So it worked. You were right. Those of you that said cosine, you were right. That equation works. Now, like the one we just got through working, I want to clear fractions. So I need to multiply both sides by, don't say 15, by x. Why x? To make the x on the right go away. Now, I'm not going to get it solved in one step like I did 3A, but take it in stages. Get rid of the fraction. So times x times x. So I get x times the cosine of 70 equals 15. But I don't have x by itself. That's okay. It just takes one more step. How do I get x by itself? Divide by the cosine of 70. So x equals 15 divided by the cosine of 70. And then we use our technology. 15 divided by cosine 70. So x equals 43.86. Now, here's the thing. We all like 3A better, right? Worked out one step quicker. Don't try to force it. Clear fractions by multiplying both sides by whatever the denominator of your fraction is. Okay? So it takes a whole nother step. That was what? Another 10 seconds? Don't miss it because you're trying to force it into being a shorter problem. All right, let's look at 3C. Still here on page 564. Says the front of the vacation cottage shown is an isosceles triangle. What is the height, x, of the cottage above its foundation? What is the length, y, of the roof? Explain your reasoning. All right, so what we have here is that triangle, and look what that angle measure is. It's 60. We've got a 30, 60, 90. Do we even have to use trig?
No.
We don't. Okay? So, kind of like when we learned 30, 60, 90, we forgot about the Pythagorean theorem. Now that we've learned trig, don't forget about 30, 60, 90 and the Pythagorean theorem. That 65 feet at the bottom, what happens to that when that altitude? Yeah, so what's half of 65? So that's 32.5. That 32.5, is that the long leg, the short leg, or the hypotenuse? Yeah, in fact, I'm going to erase this part because I'm just dealing with what's in red here now. All right, that's the short leg. So what do I multiply that by to get x?
Square root of 3.
Square root of 3. So 32.5 times the square root of 3 feet, that's x. What do I multiply 32.5 times to get y? Times 2, so I get my 65 feet back, don't I? Explain my reasoning. 30, 60, 90, triangle. But wait, there's more. Let's say you do forget our good friend 30, 60, 90. Can we still work this problem? Yeah, to get x, using this 60 degrees here, I know I'm looking for x, and I know that, so I need to use tangent, don't I? Can't I say that the tangent of 60, did I call it 65? Tangent of 60 equals opposite over adjacent. Clear fractions, multiply both sides by 32.5. And let's see what that is. 32.5 times the tangent of 60. And I get 56.29 for x. I wonder if that's what that says. Let's see if it is. 32.5 times the square root of 3. Yeah, we got the exact same answer in a completely different way. We can get y, can't we? Using that 60 degrees again. Now, don't use our rounded answer for x. Use a given length. So let's use the 32.5 and the hypotenuse. So should I use sine or cosine? $32.5, is that the opposite leg or the adjacent leg? It's adjacent. So I need to use cosine, don't I? So the cosine of 60 equals adjacent 32.5 over hypotenuse. Why? Don't get too anxious. Clear fractions. Then divide by the cosine of 60. And let's see what we get. 32.5 divided by cosine of 60. Ooh, that makes me nervous. But that's what I got that way, so it's okay.